Okay, so the plan today is to go over properties of continuous functions, and then on Tuesday, we'll move on to uniform continuity. And I think the class should probably end there. So let's start. So continuous functions are very nice. So one of it, I don't think maybe the book doesn't call it this, but it's called the extreme value theorem. And basically it says f continuous on AB and f bounded. Okay, then f is bounded. And we have more than that. It attains its bounds. So f attains its max and min values. So, a priori, remember, bounded just means the soup is finite, right? But the soup of a set might not be in the set, right? So you think of it like, okay, it's bounded, but not only that, there's some points where I do attain the bound. So there exists x naught, y naught, such that f of x naught less than or equal to f of x less than or equal to f of y naught for all x in AB. So this is pretty strong statement. So one example would be, of a discontinuous thing would be something like this, right? Okay. I don't know. Let me just make it up. A point here, and then all the way down. Yeah. So let's make this 1 and this 0. So you see that this thing is this thing is certainly, it's discontinuous, right, on AB, because it's discontinuous at whatever this point is. And you see that it doesn't attain the maximum, right? I mean, like, there's no point where the value at the point is the maximum, right? I mean, the soup, because the biggest value is right here. So continuous functions are very nice. So that's the first property. So the second property is IVT. So this is pretty important. So f continuous real valued function on interval I, then f has intermediate value property. So it means for all a, b, and I, a less than b, and y between f of a, f of b, there's some point where there exists at least one x in AB. So let me, this looks kind of weird. One x in AB such that f of x is y. So what is this saying? So let's just try to, see it by picture. Yeah, if I draw like this is A, this is B, right? So this is B, f of B. I mean, I didn't really write what f is, but remember, a continuous function is something, where you don't lift your hand off the paper, or in my case, iPad. So, I mean, if you draw any continuous function, I don't know, it could be as crazy as long as is the function, right? I don't know. Sorry, this should be curvy, like something like this, yeah? Doesn't really matter, but basically what IVT says is you have to get every value between f of b and f of a, right? So this is f of a, this is f of b, right? So sorry, maybe it's not drawn to scale. Maybe make the dot bigger. So you see, you get every value in between right here, right? So that's pretty much what IPT says. You know, no matter, and how you say you get every value in between is, you know, for any y between the two values, you obtain it, right? So, you know, and note is at least one, right? It could be more than one. So like if y was like right here, I attain it like many times, right? I attain it, let me see, once, twice, 3 times, 4 times, 5 times. So yeah, but basically saying you can't jump, right? Because here, a discontinuous function, right? If I go from, let me use another color. So if I go like from here to here and then open circle, I don't get every value in between, right? You know, I don't get values here, right? I miss all the values here. So that can't happen for continuous functions. Okay, does everyone understand IVT? Okay, so let's move on. So one of the corollaries in the sense that you can't get you have to get everything in between is if f is continuous function on interval I, then what is f of I? What does my function map? You know, this is the set of f of x such that x is in I. This thing is either an interval or a point. So that's one nice thing, right? Continuous functions takes intervals to intervals, and Ren is at a point. So Ren does a continuous function take an interval to a point. What functions do that? So anyone? So if I map everything to a point, all my values take one value, right? It takes you know the value at whatever that point is. So it's constant functions, right? So you know either f is constant or is some other continuous function in which you map interval to interval, right? Like x squared maps 0, 1 to the interval 0, 1. Okay, that was a pretty bad example. It maps like 0, 2 to the interval, you know, 0, 4, right? So it takes like intervals to intervals. Okay. So next thing, in the case f strictly increasing. So no, I need strict here. Increasing continuous on interval. So we have one thing, right? From corollary above, f of I, sorry, interval I, f of I is an interval j, right? J interval. But not only that, then f inverse is a function on domain J. Then it's saying f inverse is continuous strictly increasing on J. So question here, why do we need f strictly increasing? You know, here. What goes wrong if it's not strictly increasing? So again, let me just review. If a function f maps like a to b, the inverse maps b to a. Yeah, that's what the inverse does. So what happens if you're not strictly increased? So what's the difference between increase and strict increase? Can anyone tell me? What is the difference between increasing strictly and not increasing strictly? Anyone? The equal to, right? There's an equal to part. But so basically it's possible if it's increasing, it's possible to map like A to B, and then I don't know, like C to B, right? This is certainly not possible if you can't map to the same point, right? If you're strictly increasing, but if you're increasing, this is certainly true. I mean, this is certainly possible. But then, what is the inverse here? Like, it can't be a function, right? If the choose, does it map to A? Does it map to C? Right? Like the inverse, it doesn't really make sense, right? Because to be a function cannot map a point to two different points, right? I mean, it doesn't pass, what do you call it? Horizontal line test, or I forgot, either horizontal or vertical. But anyway, so that's basically the point of why you need the strict. So okay, anyway, so let's continue. And then there's a theorem. Finally, last thing. I wouldn't really worry about the strict part. The important thing is extreme value theorem and IVT. F is one-to-one continuous function on interval I. On interval I, then F is strictly increasing or strictly decreasing. There's a quick, proof of this, and it's by drawing. Yeah, so let's say I started at a point here. If I go to the next point, I mean, there's no really next point, but if I'm increasing here, right, if I'm going to go back, I won't be one-to-one, right? Because then 2 points will map to the same thing. So you sort of see I have to keep going up, right? Because if I ever go down, right, if I ever go back down, the one-to-one property fails, right? And same thing if I started going down. So sort of like a picture proof. And part of it is, but it's certainly not true for decreasing, right? So here, if I'm going up, right, if I'm not continuous, I could certainly, just open circle and then put a dot somewhere, right? So you see here, like continuity, you have to keep your pencil on like the page. Okay. Is everyone good with continuous functions? So we're just gonna blow through like all the questions because I don't think they're that hard. So yeah, exactly. The inverse might map to like, basically it's still somewhat defined. Like you could make a choice, right? You can say choose A, right? But like someone might ask why not choose C? Okay, so 18.4 S and R. So assume there exists xn in S going to x not in S. Not in S. Show there is an unbounded function. Unbounded continuous function. Sorry. Continuous function on F. Can anyone tell me what this function is? So it's based off the, sort of ignore this question for now. What unbounded continuous functions do you know? So let's go back up. By extreme value theorem, if I'm continuous on a closed interval, I'm bounded, right? So you should think of a continuous function on an open interval that is unbounded. So what function on an open interval is unbounded? Name me some. You should know a lot, but E is bounded. E is a constant. E is a number. So constant functions are certainly bounded because they only hit one value. Is is y equals x bounded on like some by open interval? I mean like open interval ab, like yeah, like natural log 1 over x, right? I mean y equals x is certainly bounded on like a to b. It's bounded by like b, right? So yeah, like think of ln x 1 over x, right? So 1 over x, let's sort of look at 1 over x. This is somewhat similar, right? In this case, my s is 0, 1. And there's a sequence. There exists sequence xn going to 0, where this is my x0. And 0 is not an s, right? Because s is the open interval, 0, 1. Then this function satisfies it. So this sort of gives you an idea of what should this function be. Any ideas? So, if you think we take something similar. You can do something like this, right? It's sort of like a generalization of like 1 over x. Right? This function is continuous on S. Why? Because I mean you could show it, but why is that true? Because you're never dividing by 0 on S, right? Because x naught is not an S, right? Like 1 over x is certainly continuous outside 0, right? Continuous outside 0, right? The only bad point is 0, and similarly here, right? The only bad point is like x naught, right? But x naught's not an S, so, and this function is clearly unbounded, right? Because when you get close to x naught, you're like dividing by 0, so you blow up, right? Is everyone clear so far? Okay. So let's move on. So I did 18.4. Let's do 18.6 now. So prove x equals cosine of x for some x in 0 to pi over 2. So prove x equals cosine of x for x in 0 pi over 2. All right, how am I going to do this? What should I be using? So let me rephrase the question. So to prove this, proving x equals cosine of x is same as proving sorry, for some this doesn't make sense, for some x in 0 to pi over 2. Yeah, certainly it doesn't hold for every x. Same as proving x minus cosine of x is 0 for some x in 0 pi over 2. Okay, does this ring a bell now? What should I be using? So x minus cosine x is a continuous function, right? So any ideas? Huh? So how about this? We use IVT. So x minus cosine of x is continuous, right? And what does IVT say? If I have f of a, f of b, I get every point in between, right? So one way to approach this is say, find a value where x minus cosine of x is positive. Find a value where x minus cosine of x is negative. And by IVT, you get every point in between. In particular, you get 0 because, you know, one's positive, one's negative. You know, you're going to get every point in between, right? So, you know, picture, you find a point where it's negative, a point where it's positive, then you basically get everything in between, right? So in particular, you get 0. So everyone clear with the approach? Okay. Luckily, I think we have a value. So x equals 0 is 0 minus cosine of 0. That's less than 0. Yeah, because cosine of 0 is like 1. And then x equals pi over 2, right? From here, it's pi over 2 minus cosine of pi over 2. That's bigger than 0. You don't even need to know what cosine of pi over 2 is, because pi over 2 is bigger than 1, and the biggest cosine can be is 1. So the maximum you'll be subtracting is 1. So from here, right, by IVT, there exists, so it depends on the point you choose, right? So there exists C in the 2 points you chose, 0, pi over 2, such that if I let f of x be such that f of c is 0, right? So again, let's go back. Let me just quickly go back to IVT, right? There exists x in a, b, right? So, and then a and b are like the points you plug in, right? So the interval you're in matters, right? Because if you plugged in like x equals, you know, if plug in x equals pi, and I don't know what else is there. I guess in this case it doesn't really work, but basically what I'm saying is, I don't know, something like if the question was saying, yeah, I guess in this case it doesn't. It's like increasing, but you know, you get what I mean, right? If you plug in like another value, like I'll call it pi over 3, then it's c in here, yeah. In this case, it's fine because everything past pi over 2 is always positive. But be careful about like where the c lies in. Yeah. Okay. Is everyone clear
Do we
on
have to
that?
prove that x minus cosine x is continuous?
I think that's clear enough. You could just say it.
Okay.
Yeah. So okay, so let's practice one more. So x e to the x equals 2 for some x in 0, 1. So prove x e to the x equals 2 for some x in 0, 1. So again, you can boil this down to, you can subtract 2 on both sides and show, you know, you're negative and positive. Another way is to just say, it's the same idea, right? Find the value like below 2 and find a value above 2, right? And then since e to x is continuous, you get every value like in between. So in particular, you get 2, right? It's just that you're centered at a different place. So this is 2, you know, choose a value above, choose a value below, and then you get everything in between, right? In particular, you get the value 2. So again, normally the point they give you is the one that works. So if not, you have to find it yourself. But if I let f of x equals x e to x, f of 0 is 0, f of 1 is e, and e is bigger than 2, right? E is like 2.7 something, right? So there by IVT, yeah, I forgot to put by IVT on the previous, by IVT, there exists C in 0, 1 such that f of C is 2. Yeah, oh, I did write by IVT. Okay, great. Is everyone clear on how IVT works? Okay. So we have 18.8. F of A times F of B is less than 0 for some A, B, and R. Prove there exists X between A and B such that F of X is 0. So I'm going to have to copy that. So F real valued continuous function on R. F real valued continuous function on R. And F of A is less than F of B. I mean, F of A times F of B is less than 0. And we have for some A, B, and R. So we need to prove there exists X between A, B such that F of X is 0. Okay, same exact thing, right? To show a continuous function is 0 somewhere, all I need to do is find a value that's bigger than 0, find a value smaller than 0. So what should my values be? You don't really have much choice because they don't really tell you what the function is. So there should be a one line.
F of B.
Huh? Yeah. So it should just be F of A, F of B, right? You don't really have any other point. So so you can say without loss of generality, you know, F of A is positive, right? I mean, you'll see why. It can't be 0 because if it's 0, this thing's, you know, not less than 0. So if F of A is positive, then F of B is negative, right? If not, their product would not be negative. So again, similarly, if F of A was negative, then F of B was positive. So in either case. So you're done. So by IVT, there exists, you know, C and I just like the letter C. C and AB such that F of C is 0, right? So you're done. So note, IVT does not tell you what C is, right? So nobody is saying like, you know, if I gave you some polynomial, you could find the roots without a calculator. Like IVT just says, you know, like a root exists pretty much. It doesn't tell you what the root is, right? Like it's just some point in AB. I don't know what it is, but I know there is one. Okay. Everyone good so far? Okay. So let's move on. So prove a polynomial function f of odd degree has at least one real root. So prove a function f of odd degree has one real root. Basically show there exists C such that f of C is 0, right? Okay, same game plan. Find the value above 0, find the value below 0. So what do we know about odd degree functions? How do they look like? Anyone? So how does, you know, okay, how about this? For odd degree, oh sorry, function f is a polynomial of odd degree. That was important. So for odd degree polynomial, what is limit x goes to infinity f of x, right? So, I mean, you have two cases, right? So, I mean, it's really the same, but if f of x is an x to the n plus a0, right? Where n odd. So the first case is when an's less than 0. So let's take an to be negative. Then what is this limit? Can anyone tell me?
Negative infinity.
Good. And what is this limit?
Positive infinity.
Good. And do you all see what's next? The goal is to find something positive and something negative, right? So you could show this, right? Since limit x goes to infinity, f of x is negative infinity. There exists a and r such that f of a is bigger than 0. And since limit x goes to infinity, f of x is positive infinity, there exists b and r such that, whoa, sorry, f negative infinity, I need less than 0, right? Such that f of b is bigger than 0. And then you're done, right? So there is by IVT, there exists C and AB such that f of C is 0. Yeah, and hopefully the second case is clear, right? So it's when your constant term is positive, but it's the same idea, right? So and odd, and this time an's bigger than 0. So without loss of generality, an's not 0 because I mean you always write the leading term, right? I mean nobody writes like x squared as 0x cubed plus x squared, right? You always write the highest order term as like the non-zero one, right? So this case true. So from here, same idea, right? Limit, except this time the limit goes the other way. I mean the value goes the other way, right? X goes to infinity, f of x is positive infinity, and limit x goes to negative infinity, f of x is negative. Basically, odd functions always look like this, right? Like x cubed, they always go opposite direction, right? Like this goes up, this goes down, right? So that's the way you should think of it graphically. So again, since equals plus infinity, there exists a and r such that f of a is bigger than 0. Since limit x goes to negative infinity, f of x is negative infinity, there exists a and r such that, b and r such that f of b is less than 0, right? And then by IVT, there exists C and AB such that f of C is 0. Everyone clear? Hopefully that's enough IVT practice. I think there's more, but okay. Let's just do one more maybe. So let's just do 18.10. Yeah. So f continuous on 0, 2, and f of 0 equals f of 2. So show there exists xy where y minus x is 1, and what was it? So and f of x equals f of y. So the hint is to consider g of x equals f of x plus 1 minus f of x. So obviously, if y minus x has norm 1, you could think of like, you know, or if you like x minus y has norm 1, x as like y plus 1, right? Or like y as x plus 1, right? So you should think of this like your y. So again, to show they're equal is the same as saying f of y minus f of x is 0, right? So it's the same as saying, so again, we need to find values where g is bigger than 0 and g is smaller than 0. So can anyone, so obviously you don't have much choices here because, we don't even know what the function is. So one thing we can do is just plug in points, right? So g of 0 is what? So note g is continuous on 0, 1, right? Because f is continuous on 0, 2. So g of 0 is f of 1 minus f of 0. G of 1, right? I can't plug in 2 because it's a function on 0, 1. So I mean, the best thing you could do is try the endpoints. Is f of 2 minus f of 1. Now what can anyone tell me? I don't know what the signs are, but what do I know about these two? What are their signs?
One is positive and the other is negative.
Yeah, one is positive, one is negative, right? Because f of 0 is equal to f of 2. So let me just write, this is less than 0 without loss of generality, and this is bigger than 0. Yeah, it could be the other way, but we don't really care, right? So by IVT, there exists C in the 2 points I plugged in, 0, 1, such that g of c is 0. But g of c being 0 means g of c equals f of 1 plus c minus f of c is 0. So we just found it, right? This is my x, this is my y. Yeah. Everyone clear? Maybe this is a bit more tricky, but okay. Is everyone clear? Okay,
I have
so
a question.
Sure.
So I think we still need to consider a special case when f1 equals to f0 equals to f2.
Oh yeah, I mean, if f of 1 equals f of 0, then this is your x, this is your y.
Yeah, right.
Yeah. Yeah, sure. Yeah, but if they're equal, then you're also done. So okay. Any questions? So that's it for this session. So I sort of want to. I know your professor probably didn't go over uniform continuity yet, but I sort of want to give you all intuition so you can understand. Because it's going to be very confusing because a lot of you are going to think is the same as continuity. So let's sort of work it out. So let me show. Let me think. So show x squared is continuous at 0. How would you show this? Question. How would you show this? So again, I want to show for all epsilon bigger than 0, there exists delta bigger than 0, such that if absolute value of x, because it's x minus 0, right? So absolute value of x is less than delta, absolute value of x squared is less than epsilon, right? So what should my delta be right here? Can anyone tell me? this should not be hard. So so I mean, it's pretty easy to relate these two. One of them's the square of the other. So yeah, square root epsilon, right? So let epsilon be bigger than 0. Choose delta equals square root epsilon. Then if absolute value of x is less than square root epsilon, absolute value of x squared is less than epsilon. And then you're done, right? So should be fairly easy, right? So, but now here comes the issue. The question is, so hopefully, you know, the same delta, you know, we clearly know x squared is continuous, right? So the question is, does delta work for x squared continuous at 1? Yeah? So I can simply ask the same question, right? Is x squared continuous at 1? But I could ask something more. I could be like, okay, maybe it is continuous at 1, but is delta the same, or does delta change? So to show it's continuous at 1, I need to show for all epsilon bigger than 0, there exists delta bigger than 0, such that if x minus 1 is less than delta, so in my case, I need to check, does root epsilon work, right? Epsilon, then x squared minus 1 is less than epsilon, right? So this is the question, right? If I shift my point, does the same delta work? Does anyone have an answer for this? So this is actually not true, right? Because take, I don't know. What should I take? Take epsilon equals 4. Then if x minus 1 is less than, you know, what's square root of 4 is 2. Then want to show if this is true, then x squared minus 1 is less than 4. But this is not true, right? Like choose x equals, I don't know, what's the number, 2.999. Yeah, so this number satisfies this, right? It has distance like 1.999 from 1. But I mean, you could check that 2.999 squared minus 1 is not less than 4, right? Because 2.999 squared is pretty much like 3 squared, and 3 squared minus 1 is 8. Yeah, so you sort of see that the same delta doesn't work, right? So for continuity, right, delta depends on epsilon, right? Because here, you know, someone hands me epsilon, and then right here, someone hands me epsilon, and then I choose my delta, right? So delta should always depend on epsilon. But here, delta depends on your x, right? It depends on this thing. It depends where what you want to show is continuous at. So for continuity, delta depends on epsilon, and I'll call it x, right? You know, the point you want to show, continuity, right? So uniform continuity is, you know, you could ask, right? You know, a function if delta depends only on epsilon, right? So basically it's saying the same delta will work even if I shift my point. Yeah. So that's the idea of uniform continuity. Like it holds no matter what my point is. Right? If I'm uniformly continuous on like closed interval 0, 1, 1 delta should work for all points on 0, 1. Is everyone sort of clear on this? So of course, right, you can show x squared is continuous at 1, right? So let's assume you have your new delta. but then you could ask, oh, does that work for x squared at 2? And you'll see it doesn't. So, but yeah. Anyway, so that's sort of the idea, right? And it turns out that continuous functions on closed intervals are uniformly continuous. But that's the idea of uniform continuity. It's, you need a delta that works for every point. Okay, that's all I have for today. Any questions? So, because I know your final has like tons of uniform continuity. So on Tuesday, we'll just go over tons of examples of uniform continuity. So we're all familiar with that. Okay. By final, I meant sample final, by the way. All right. Thank you.